And to do that, we need to recall our definition of sine theta. And remembering that sine is all to do with the y-coordinate of the point on the unit circle. And so we see how sine changes as theta changes. And so using this idea, or this definition of sine, we're now going to look at actually creating the sine curve. So as the angle gets larger, sine gets larger, then smaller again, back down to 0, down negative to -1, and back up to 0. And in one rotation of the unit circle, we see this relationship occurring between the value of theta and the value of sine theta.
Okay, so does that make sense? That's what you did yesterday. You basically took a piece of string and you started it around your circle, like the circumference of the circle. And then you cut it at 0 pi and you unrolled it in what direction? Counterclockwise. So if I had pulled it from the other direction towards the left, that would be clockwise. And those angles would all be negative. So negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. The wave is continuous in either direction. So there are two pretty common applications of a sine wave. When it comes into an application problem, we call it a sinusoidal graph, which is kind of a cool word. So think about temperatures. If I wanted to track the temperatures in 1 year, what would the period be? 1 year, 12 months. And I would divide my increments into 4 parts, and I would graph either the highs or the lows. And what I would actually find every time is a sine wave, or a cyclical graph like the sine wave. In middle school, did you guys do springs at all? No. How about in science here? You never talked about springs and how those are sine waves or cosine waves?
Oh, yeah.
With amplitude, so if you have a spring and it's really close together, that's a lot of rotations in one period, but if it's far apart.
Yeah.
Okay, so I'm sure you talked about maybe sound waves. Okay, those are real life applications of these trig functions. All right. So she also does one for cosine. Let me just get it to where she's going to do that. There we go.
In that green line, we see how the value of cos changes as theta changes.
It's not really cos.
And now if we use that definition to create our graph, we see that cos starts out at 1, decreases down to 0, out to -1, increases back to 0, and then back out to 1. And again, we have the same situation with the sine curve. We could lap around again and see this exact same pattern occur again.
Okay, so we could keep going infinitely in either direction, which is why the domain is all our numbers, either direction, counterclockwise or clockwise. It's just going to depend on the angle, if it's going to be positive or negative. I see the valley. Where's the peak? On the end. So I've got part of a peak on the left and part of a peak on the right. And if I put that together, that makes a peak and a valley, which is what I see visually when I look at the graph. I know that I've gone one period if I've seen a peak and a valley. Okay, so we're just going to practice from scratch graphing sine and cosine, right? So this is where you need some paper. We're going to do it like you are just now practicing for the first time, applying what we did yesterday. Okay. Where x is just an angle. Okay. And so the way that we graph it is very similar to what she did. We're just unrolling it along the x-axis. And so there are some things that we need to label every time. We're doing the parent function. So where is the midline? Y equals 0. And that's how we need to label it. We don't put 0, we put y equals 0 because it's a line. Okay, then we need to apply the amplitude. So we're going to go up to y equals 1 and down to y equals -1. Okay, there is no phase shift, so it starts where? 0 pi. And the period is 2 pi. And all periods get divided into 4 equal parts. Why is that? The quadrants on the unit circle, the quadrantals on the unit circle, there's 4 of them. We're going to divide every period we do into 4 equal parts. So the easiest way to do it is split it in half, and that becomes pi, and then do that again, and we have pi over 2 and 3 pi over 2. And then I think we did sine in green yesterday. So where does the sine graph start, the parent function? At the midline. That's how we say it. We say at the midline is where it starts. So we graph this, and then we graph by pattern because it's so easy. So the sine graph goes up first. So we go to a peak, then the midline, then a valley, then the midline, and we graph the sine function. Always arrows on the end indicating the direction it would be going. Now I have a question. What if you had to graph this and you could not remember the pattern of the points? Is there a way for you to recreate those ordered pairs that we just graphed? You can actually make a T-chart. That's exactly right. You make a T-chart and you start here at 0 pi. What is the sine value? You plot that point. At pi over 2, what's the sine value? You plot that point, etc. All the way through till you get them all in there. Okay? So don't worry if you can't remember what the pattern is. Just make a T-chart and put it into the equation. I do not suggest doing that part in the calculator because the calculator is not going to give you exact values. Okay, so make sure you do these based on what you know about your hand. Any questions about the parent function for sine? Okay, good. Let's do one for cosine. We do cosine in blue. All right. Looks the same, doesn't it? The grid. So I still have y equals 0 as a midline. And then I'm still going to go up as high as 1 and down as low as negative 1. A little bit misspaced. Okay. And where does it start? 0 pi. Goes all the way to 2 pi. Halfway is pi. Bet you know the quadrantals now, right? We've done them so many times. Okay, cosine starts different though. It doesn't start at the midline. Cosine starts up high. So we start up high, and then what? Midline, and then low, and then mid, and then... And so the thing about the graphs is, in one period, you start and stop on the same level. So if you start at the midline, you end at the midline. Keeping in mind that these graphs are going to go in those directions at the end. Okay? Any questions on sine or cosine graphs? Good, because now we need to apply the transformations. Every single thing that we do, that's terrible, every single thing that we do comes from what we learn about sine and cosine. We build secant from that, we build cosecant from that, and we build tangent and cotangent. So if we can do these, we're home free. Okay? I posted this next file in eClass. Many of you may already remember a lot of this based on polynomial transformations. So let me just take just a minute. I'm going to insert a blank page in here. And ask if you remember, what is that? It's a quadratic function. It's a parent function for a quadratic, right? It's a stretch. What kind of a stretch? A vertical stretch. If that had been less than, it would have been a compression. It would have been short and squatty, right? Okay, what about this? Horizontal translation. Which direction? To the right. Excellent. Reflection over the x-axis. Vertical stretch by 2. Horizontal shift left 3. And then down 4. The whole thing shifted down 4. Okay, if you can do what you just did, then you already know how to do transformations with trig functions because they work exactly the same way. They're even in the same location in the graph, located around the trig word. Okay? So, I know this is a little overwhelming looking at it this way, but I put everything on here. So, the right-hand side is for secant and cosecant. Ignore that for right now. And let's just look at these parts. This is for sine and for cosine, and I know that some of you learned it last year, and I know you were showing me Kamal with the ABCD. Did anybody else learn it with the ABCD? How about the H, C's, and K's? Okay, so I've got both on here. It doesn't really matter which way you learn it. You keep doing it the way you were doing it. It applies the same way. So we'll start with the A. The A is the amplitude. The amplitude is the same thing as a vertical stretch or compression. When we list the amplitude, we always list the absolute value. Then why sometimes do we go up to 1 and down to -1? If it's always the absolute value, how did it become negative? What'd you do? You flipped it. You reflected it. That's what that negative is from. Okay? All right, so the period. In the parent function, the period is just 2 pi. But that's because the b or the k value, depending on how you learned it, is 1. But if the b or the k value is something different, it changes the amount of space it takes to make a peak and a valley. Maybe it takes a smaller amount of time to make a peak and a valley, and I can make a bunch of them. Or maybe it takes a really long time to make a peak and a valley. That's the period. All right, the phase shift. What does the phase shift do? It's your starting point. So for the parent functions, the phase shift was at 0 pi. But what if I don't want to start there? What if I want to move the graph and start it at pi over 2? Can I do that? All right, so look at this from yesterday. This is Lee's graph from 3rd period. Remember, the green was the sine graph and the blue was the cosine graph. Okay? Both of them start at 0 pi, no phase shift. But what if I wanted you to translate the sine graph so that it is the cosine graph? What do you need to do?
Oh, horizontal shift to the left.
Make a horizontal shift to the left. How much? Pi over 2. What if I wanted to make the cosine graph the sine graph? I need to make a shift horizontally to the right, pi over 2. What if I reflected the sine graph over the x-axis? Would that make it the cosine graph? No. But if I reflected it and shifted it, then it would be the cosine graph. So that's basically what you're doing. I can give you characteristics. I can give you amplitude, phase shift, period, whatever. And you should be able to write a graph either in terms of sine or cosine, as long as you keep those transformations in mind. So the sine graph is the cosine graph and vice versa if what? If I make a translation horizontally of plus or minus pi over 2. Okay. Vertical displacement. Vertical displacement is your new midline. You told me before that it shifted the graph up or down. It shifts the vertex up or down. Well, we don't have a vertex in these. We have a new midline. Your vertical displacement is your midline. Your phase shift is your starting point. Why did I put negative here? Why is it negative c over k or negative c over b? It's the opposite of what you think in parentheses, because when you take it out of the parentheses and solve it, you move it over across the equal sign. That changes the sign of the value. Okay, this is much easier to understand in application. you'll know what to do when you see the graph, okay? So let's just try some graphs. We're just going to be graphing, I don't know, maybe 5 or 6 different functions today. I think we do everything but a phase shift today. Tomorrow we'll do the phase shifts. We'll start out a little bit slower. So, here's my first example. This is also on E-class. It's just kind of a little reminder, but we're going to start with this one. Y equals 2 sine of theta. First, y equals 2 sine of theta. Does anybody have an idea of what the graph will look like when I get it finished? It's just going to be taller, right? By how much? 2 units instead of 1 unit. Anything else change? No, not at all. But instead of calling it a vertical stretch, we're now going to call it the amplitude. So we start here. The amplitude is 2. It's always positive. Does it have a vertical translation? So we just put in A. What about the period? Does the period change? So then it must be 2 pi. If it doesn't change, it is what the parent function is. What about a phase shift? None. Now you can't leave those blank. You have to put something there. So NA is the appropriate response. Okay, so now let's graph it and see what it looks like. All right. What is the midline? Y equals 0. What's the max? Y equals 2. What's the min? Y equals negative 2. No phase shift, so it starts 0 pi. Period is, so I come to the end and I'll label 2 pi. Period gets divided into 4 equal parts. So go halfway, there's pi, and then go in between those, pi over 2, 3 pi over 2. Okay, now the sine graph starts where? At the midline. Then what? Then your max, mid, min, mid. Starts and stops in the same level. Okay, arrows on either end indicating that we just are looking at a small snapshot of it. What if you forget the pattern? Plug it into a T-chart. So you start out at 0 pi. What is the sine of 0 pi? What's 0 times 2? 0. Let's do the next one. What is the sine of pi over 2? What is 2 times 1? 2. That's how you know how to make the ordered pairs. We follow a pattern because it's the same pattern every time. Okay, now I want us to look at these in the calculator. So take your calculator out. We're going to do some stuff to it to get it set up first. First thing we want to do is always be in radians. We are finished speaking Babylonian. We do not need degrees anymore. We will rarely work in degrees. If you want to think in degrees, that's fine, but you need to convert to radians, which means that all your answers will be exact. Okay? So we go first and we change the mode of our calculator. So hit the mode key. Your calculator should be in radian. Okay? That's step number 1. Step number 2, you don't have to do this every time, but remember when we did the stat unit and we were putting in data into the list? We want to make sure that the stat plots are turned off. So it goes second, y equals, hit the number 4, that should say plots off, hit enter, and it should say done. Now nothing that you have in there will interfere with your graphs. Okay? So now go to y equals. Let's start out with the parent function. So the parent function for what we just graphed is sine of x. So sine of x. Close it out. Got it? Okay. Now, Now, if you don't have an update on your calculator, there is still a way for you to differentiate the lines. Do you know how to do that? Okay, so let me show you. Come down to the next line and scroll over as far left as you can go. And then hit enter. And what it does is it changes the texture of the line so that you can tell graph 1 from graph 2 from graph 3. You can do that every time. There's several different options. Some are thin, some are dots, some are really broad. You can change, if you have a color graph, then it's automatically changes the colors. Okay, so now in Y2, let's put in that function. What was the function? 2 sine of x. 2 sine of x. Close it out. Okay, so what I want you to do at this point, zoom. What do you think? Which option? Zoom trig. Zoom? Is that what you're telling me? Is that what you're asking? Yes. Zoom 7. Okay, now, so my question is this. I hit a zoom 7, and that graph does not look like what we graphed together. So can you tell me what we are looking at? We're looking at 2 periods. On this graph, we're looking at from here to the right is what we have. Well, what's all this to the left? That's going clockwise around the unit circle. So it's going back to negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. But I want to see all that. So what should I adjust? Okay, so hit your window button. Now, we know right now that we're dealing with a starting point of 0 pi. So let's change our x-min to be 0 pi. And you'll see it's going to take the pi out of there in just a second and make that just a 0. Now, what should our x-max be based on what we've just been doing? 2 pi. So 2 pi. Now, what number should be there? 6.2. There you go. And that's because that's 2 pi. What should our scale be? Pi over 2. Why? Because that's how we did our scale. We did it in pi over 2. So we're going to go pi divided by 2. Okay. It doesn't really matter what our x-min and x-max are now, but later we may have to change that. But for right now, this should be fine. Okay, so let's hit graph again. There's our parent function. Now does it look like yours?
Yeah.
Okay, and there's our transform function. And now we're just looking at from 0 pi to 2 pi. Does it match what you have on your paper?
Yeah.
Beautiful. So the point of the calculator is not to do the graphing, it's to check the graphing. Check to make sure that you've done the graphing correctly, that your shape of the graph. It's also very helpful on those multiple choice on WebAssign, where it gives you a function and tells you to pick out the graph. Now you know how to do it. You need to be able to look at the grids that they give you and adjust your viewing window. It's like taking a photograph. You have to decide where you want everybody in the picture to be, and then you have to adjust accordingly. Okay? All right, so let's keep going and try the next one. So this next one is sine of theta plus 2. So I want you to imagine what is going to happen to this graph from the parent function. It's going to travel up 2 units. Okay, well, let's start from the beginning. What is the amplitude? 1. What is the vertical translation? Okay, you can either write the word up and then a 2. You could write the word down 2 if it were down. You could draw an arrow up or an arrow down. Or what else? Plus 2 or minus 2. But you can't just put 2. 2 doesn't give me a direction, and a translation is a direction. Okay, period. 2 pi. Any phase shift? Nope. You can't leave it blank either. You have to tell me what the phase shift is. If there's not one, tell me there is none. Are we ready to graph?
Yeah.
Okay, so same thing. So my new midline,
Y equals 2.
it's now y equals 2. What's my new max?
Y equals 4.
Y equals
3.
3. And what about my min?
Y equals 1.
Y equals 1. Start at your midline and apply your amplitude. Our amplitude was 1, so from the midline we went up 1 and down 1. Okay? We have no phase shift, we have no period change, so 0 pi to 2 pi. Alright? Sine graph starts at the midline and then does what? Max, mid, min, mid. Okay, now I want you to compare just by looking at those two graphs. I don't want you to look at the scale, I just want you to look at the graphs, picture the graphs. What do you notice? They look the same. This is a fault in the method of graphing. The way that we graph makes it appear as if all the graphs look exactly the same. The only way to go beyond that is to do it on one piece of graph paper and adjust along the way. Like take one piece of graph paper, you could probably fold it into fourths and make your coordinate plane out of one piece and then graph everything from there in those units. Then you can see the differences. The other thing that's critical is that you actually have to look at the scale. The reason I want you to do it in the calculator is because I want you to see how the changes are made. So go back to your calculator and go back to y equals. And now let's do this one. It was just sine of x plus 2. So sine of x plus 2. The graph. Now can you see how they look different? Started out with the parent function, it's blue. Move to the transform function with the vertical stretch, and that's red. Move to the vertical translation up to, and that one is in black. Now you can see that they really do look different. I just don't want you to get the idea that all of the graphs are really the same graph. They're not. It's just the way that we graph. It's the fault of the method that we use for graphing. Okay? All right, any questions so far? Feel like you got this? Awesome. Let's keep going. So the next example that we have is cosine. What do you notice about this equation? Look at the very first thing you see. Reflection. It's a reflection. So usually when I'm doing these myself, I either highlight or underline or circle the reflection because I need to be reminded to go back and apply that when I'm graphing. All right, so what is the amplitude? It's 3. Amplitude is always positive. It's not negative. It is an absolute value of that A value. All right, what about a vertical translation? So either -2, down 2, an arrow down 2, whatever your indication is, but it has to include a direction. It can't just be a number. All right, what about a period? Still 2 pi. And have I made a phase shift? No. So, and this is an indication that I'm starting at 0 pi. I'm ready to graph. I've got all the parts. So what is my midline? Y equals -2. So here we go. Y equals -2. But my amplitude is 3. So I'm down at -2. I need to add 3, and I'm at y equals 1. And if I subtract 3, I'm at y equals -5. Got that done. Okay, starting at 0 pi again, finishing at 2 pi, always dividing into 4 equal parts. Okay, let's back and reflect. I'm not doing sine anymore, I'm doing cosine. Cosine graph starts at the max, but it's flipped. So it starts at the minimum. So I start at the minimum, go to the mid, go to the max, go to the mid, and mid. Starting and, ooh, that's terrible lag, finishing on the same level. Okay, let's put it in our calculator, see what it looks like. So let's go to y equals first and clear out what we have here because we don't want these sine graphs in our way anymore. And let's do cosine. Just cosine of x. Okay. Let's do this particular transformation was -3 cosine of x, and then what? -2. Okay. If I hit graph, here comes my parent function. I like that. What do you think about this? The picture that we have, the window that we have. Are you happy with it? I'm not happy with it either. I'm not happy with it because I know based on my graph that it goes down to -5, but remember the window we had originally? It only went down to -4. So go into your window, and I usually go 1 or 2 above or below where I need to be, just to kind of give me some viewing space. So I'm going to change this to -6. Do I need to change the max? No, I can if I want to, but it's not necessary. So I hit graph, and there's my parent function again. Now can you see what you want to see? You see that it actually started low at 0 pi -5. Okay, let's just do something else. Let's go second graph. That takes me to what? The table of values, they are the ordered pairs. So the first thing that you see is x, and the x's are all angle measures. So at x is 0, your y value is -5. That's just a good way for you to get an idea of where your graph is hitting a high point or a low point. The first y will be for the blue graph, which was our parent function, and the second y will be for our red graph, which was our transformed function. Okay, just different ways of figuring out where you are on your graph. All right, so we got the last one that we're going to do, and it's kind of the hardest one, well, because it's got a little bit of a shift. So tell me what you know about this one. Has an amplitude of 2. Stretched, vertical stretch by 2. Good. How about a vertical translation? Not one, so NA.
Oh, is it?
No. The period is 4 pi. Small is right. All right, so here's what we have to do. We go back to our sheet, the graphic organizer that told you where all the parts are. Okay? If there is a change in the period, a number will be beside your angle notation. What number is beside your angle notation? It's 1/2. That's theta over 2, or 1/2 theta. Just like pi over 2 is 1/2 pi, So the b value is 1/2. So your formula says period equals 2 pi over b, or 2 pi over k, depending on how you want to think about it. And in this particular example, b is 1/2. So 2 pi divided by 1/2 is really 2 pi times 2, which is 4 pi. So our period is 4 pi. All right, what about a phase shift? Not one. Okay. Space. Chart grid. Do I have any sort of a vertical translation?
No.
No. So where's my midline?
Y
equals 0. How about an amplitude that I need to apply? Up to, so my max will be at y equals 2, and my minimum at y equals -2. Do I have a phase shift? Nope. So this starts at 0 pi. Where does it end? 4 pi. A period gets divided into 4 equal parts. So the method that we use is simple. We first split it in half. That's 2 pi. And then we split each of those sections in half again. So what is this? That's pi, and that's 3 pi. Have we taken care of all the transformations on this grid? So now what? We apply what we know about cosine. There's no reflection, so it starts high, mid, min, mid, okay? Now, does that look like yours? Does that look any different than the parent function that we graphed? That's the fault of our graphing method. It's not to say that we're graphing it incorrectly. It's just a flaw in the graphing method. You are graphing it correctly, but it is a flaw in the way that we do it, in that it makes everything look the same. So, we take care of that by coming to our calculator, going back to y equals. All right, so this graph was 2 cosine. Was it x over 2? So x divided by 2. Anything else? Okay, now we're going to hit graph, and we're going to have a problem. What is my problem here? I can't see it, so I need to adjust my window. So I go back and I hit the window key. I need to make my x max 4 pi. So 4 pi. Do I need to change my scale? I mean, maybe because the scale that we just used wasn't half pi, the scale we just used was pi. So let's make it look like what we're doing. So that's pi. Anything else I need to change? It's okay if the y's are a little bit off. We can still see what we need to see. Now let's hit graph. Okay, now tell me what happens with the first original function. It doesn't look the same as it did anymore. There's 2 periods now. It was 2 pi. We extended it to 4 pi, so it graphed 2 peaks and 2 valleys. It did the same thing for the red graph. Now that the black graph is coming in, this last function, where we change the period, now you can see what looks like our graph. So can you see how helpful the graphing calculator can be as long as you know how to work it? You need to be able to look at it and say, you know what, the viewing window is not quite right, and how do I adjust it? Do I need to adjust the x's? Do I need to adjust the scale? Do I need to adjust the y's? Exactly what is it that I need to do? Okay? Any questions? We're going to stop there because that's the last one before we start making phase shifts.
Look at the scale.
Oh, so if you want me to go back in window? Okay, so your x scale is your intervals. So you see how that value is 3.14? That means our intervals are intervals of pi, which is what we use. When we were doing the parent functions, we were using intervals of half pi, which was 1.57. Okay, so your scale for either x or y just tells you how wide your intervals are, and they always need to be the same width. Okay, equal width for 4 equal parts. All right, any other questions? Okay, good. I need to know if you guys,